Does the following make sense? So here's the scenario. When the student was asked how she felt about the last exam, she responded with, and this is a summary of how she responded. She felt like there was a 0.5 chance she got an A 0.3 chance she got a B, a 0.2 chance she got a C, and a 0.2 chance that she failed. Now this is the entire sample space. We are excluding D from the calculations here, so it's either A, B, C, or fail. And I'm going to say this does not make sense. If you add up all of the probabilities of the entire sample space, it should equal 1. But if you add up all of these probabilities here on the right side, you get 1.2. And that doesn't make any sense. The probabilities can only ever add up to 1 in a given distribution. To prove this again, or a different way, we can think of the 0.5 probability as a 50% chance of happening. A 0.3 probability is a 30% chance, a 0.2 probability is a 20% chance, and the 0.2 again is 20%. If you add up all of these percentages, that's 120%. Well, nothing happens when 120% of the time. You can only have up to 100%. So this scenario doesn't make any sense. If you want to see something that could make sense, it would look something like this. Maybe something like this here in the blue column, 0.5, 0.3, 0.1, and 0.1. All of these probabilities add up to 1, so that is a scenario that could actually happen. A meal deal at a restaurant offers 14 appetizers, 6 entrees, 5 desserts, and 8 drink options. So the question is, how many different meals can be ordered? Well, you could try to list out all 14 appetizers, and then all 6 entrees for all of these 14 appetizers, then 5 desserts for all of those previous ways to order, and 8 drinks. It's a lot to write out. We don't want to do that. Luckily, we can use the counting principle, aka the multiplication principle, that said if we consider each of these things as a different experiment, we know that we can find out the total number of ways that these 4 experiments can happen if we consider the total number of ways for each of them individually. So we can have 14 appetizers, we can have 6 entrees, we can have 5 desserts, and we can have 8 drinks. And if we take all of these numbers, these options, and multiply them together, we can get the total number of meals that can be ordered, the total number of different meals that can be ordered, which is 3,360 different meals. And that is a lot of different meals. I would not want to list out 3,360 different orders that could possibly happen. And again, the point for doing this, in knowing how many different ways this can happen, is that this now gives us a basis for starting to compute probabilities. So being able to understand this multiplication principle, aka counting principle, is very, very useful. All right, when tossing 4 coins, find the probability of getting 1, 3, or 4 heads. Okay, so this is going to take a little bit of work. And so I am going to take the time to write down all of the possible ways that you can flip 4 coins. Here they are. So here are the 16 different outcomes you could get. When you go flip the first coin, you could get a heads when you flip the second coin, you could get a heads when you flip the third coin, you could get a heads when you flip the fourth coin, you could get a heads. And I went through and I created an entire list of all of the possible combinations that could happen when you flip 4 coins. They're here, trust me. All right, so now what we should do is build a probability distribution. And what we are looking for here is heads, the number of heads we get when we flip 4 coins. So what I'm going to do is I'm going to, let's say, first figure out or write down that there are 16 possible outcomes. From these 16 possible outcomes, I want to find the probability that I get 1 heads. So I want the probability of 0 heads. I want the probability of 1 heads, and so on. And in order for me to find out all of these probabilities, I actually have to go through and do some counting now. So how many different ways in this list show up with no heads in them? And I will tell you, at least this first one, that there's 1, and it's right here. There's only 1 way you get no heads. So the probability that you get no heads would be 1 out of 16, because there's 1 way to get no heads out of the 16 possible outcomes. Now I'm going to stop here. You can pause the video. I want you to fill in the rest of these probabilities here. So hopefully you gave this a chance and you got the following probabilities. All right, so I'm going to circle these ending probabilities in blue. And yes, if you decide to add all of these probabilities together, you will get a total of 1. So now what we need to do then is figure out what is the probability that we get 1, 3, or 4 heads. Well, this is a little different. So I did something extra here with creating the probability distribution. And I think we can see it's going to be pretty easy to find because there are 4 ways to get 1 heads. There are 4 ways to get 3 heads, and there's 1 way to get 4 heads, right? So I can just add those outcomes together. We have 4 heads, 4 ways to get 1 heads, 4 ways to get 3 heads, 4 and 4 is 8, and 1 way to get 4 heads, 8, and 1 more is 9. So way down here, the probability to get 1, 3, or 4 heads is 9 out of 16, and that is simplified already. So this example encompassed 2 different things. We created a probability distribution over here. The probability for getting all the different outcomes of heads, you could get 0, 1, 2, 3, or 4 heads. So here are all those probabilities. And we answered the question that was asked. So here we have the probability of getting 1, 3, or 4 heads was 9 out of 16. And again, we could have come over here in a different color there and computed that. Let's see, so 1, 3, or 4 heads. So we could have counted, well, there are 4 heads. Does this one have 1, 3, or 4 heads? Yep. That one has 3 heads. Oh, this one has 2 heads. We cannot include that one. The next one has 3 heads. Let's include that. The next one has 2 heads. We cannot include that. The second to last one has 2 heads, and the last one has 1 head. So we can include that. So then we just come down this second list here, and I could count again. So I've got 3 heads here, only 2 heads there, 2 heads there, 1 head we're good with, 2 heads, 1 head, 1 head, no heads. And we could have counted just from our list. But since we had already created a a probability distribution over here, we could have just added the 4 over 16 plus the 4 over 16 plus the 1 over 16 and gotten the same results. Okay, this example has got 4 questions to it, 4 probabilities. You can see down here. But before we get to that, I want to talk about the standard playing card deck. And that is this over here. All of these are parsed out nicely here. So we have the sample space already given out for choosing a card from a deck. Something that I need to state out loud here is that in a deck of cards, there are 4 suits. And each suit is equally likely, has an equally likely probability of being picked. So the 4 suits are hearts and diamonds. Those are both red and I guess symbolized by a heart and a diamond. And then we have spades and clubs. These suits are black. And this is the symbol for a spade. It's kind of like an upside down heart. And this is the symbol for a club. I think of it like a little tree almost. So there are 13 cards in each suit. Oops. 13 cards in each suit. And there are 4 different cards of each value. So each card here, there's 4 different cards of an ace. The ace is at the value of that card. There's the value 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and king. And you can see that there are 4 of each of those. 2 red, 2 black. The final thing I think I need to say here about these list of cards is that the jack and queen and king of each suit are considered face cards. And that's because if you had a deck of cards in front of you, these 3 cards are traditionally printed with, I guess, people on them, and they have faces, so we call these face cards. Everything else just has like the number, the value of the suit on it. So if you picked up a 6 of spades, there would be 6 spade shapes listed out on that card, no faces. All right, so now we can start answering some questions. I guess one other thing in total, there are 52 total cards in a deck. So the sample space is 52 cards big, and you can go through and count these. I'm not going to. So we want to know the probability of drawing a 6. Well, we just have to look here. I count that there are 1, 2, 3, 4 6s. So that leads me to a probability of 4 over 52. But this is where the probability of cards becomes very interesting, and it can be semi-frustrating if you're learning it for the first time out there. This fraction can be reduced to 1 over 13. And you can see that if you divide both of these numerator and denominator by 4, then you'll get 1 over 13. All right. Next, we are going to check out the probability of drawing not a heart. So that means we can draw anything else. And I don't know if you have looked up here recently. That's a lot of stuff. So what we can do instead here is say this is equal to 1 minus the probability of drawing a heart. And that is easier to figure out. It's almost always easier to figure out a probability of something you're looking for than what you're not looking for. So we know that there are 13 hearts up here, as there are 13 cards in each suit. And there are 52 total cards. So this would be 1 minus 13 over 52. And to create common denominators, I would say 52 over 52 minus 13 over 52. Now we can just subtract the numerators from one another since they have a common denominator. So I'll have 52 minus 13 gives me 39 over 52. And you can divide the numerator and denominator here by 13 each and get 3 over 4. All right, next, we want the probability of drawing a face card, the probability we draw a face card. So these are these cards over here, as I mentioned earlier. Well, you can see just by counting, there will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 face cards out of 52 possible cards. So 12 over 52 is the same thing as 3 out of 13. Again, if you divide the numerator and denominator by 4 here, you'll see that it'll be 3 over 13, and that is as simple as it gets. Lastly, on this page anyway, we want to know the probability that you draw a black ace. So you can see here that we have 4 aces, but only 2 of them are black. So we have 2 possible outcomes out of 52 total outcomes. And if we divide both of these by 2, we'll end up with 1 over 26. This question, oh boy. What is the probability a randomly selected person has a birthday in March? What about April? Well, this brings up the very, very good point that March has 31 days and April only has 30 days. And this presents a problem when you are trying to figure out the probability. Normally, you would think, well, March is 1 month, there are 12 months, so you would think that the probability of being born in March would be 1 out of 12, right? There are 12 months. But we cannot say this. We can't say this because March has a different number of days than some other months, just like April has a different number of days from some of the other months. The most famous example is February. February only has 28 days, and it has 29 days if it's a leap year. So even February, depending upon a given year, can have a different number of days. So we have to consider how many days there are in the month divided by how many days there are in the year. And then we have to see if it simplifies. And this one does not simplify. And yes, we assume that it is not a leap year. We assume 365 days in a year. So the probability the person is born in April is 30 out of 365. Well, both of these numbers are divisible by 5, so we can simplify this to be 6 over 73. Chris Paul has made 14 of his last 38 three-point attempts. What is the probability he will miss his next three-point attempt? All right, there's a lot to unpack here. The first thing I want to point out is that this made 14 of his last 38 three-point attempts. That is something that actually happened, that has been witnessed, even though the scenario is made up. This is something that happened. So we would call this an empirical probability. And so we would say the probability, we have a three-point attempt made would be 14 out of 38. And this can be reduced here to 7 over 19, and that is as far as it can be reduced. So you would think that your answer would be 7 over 19. That's the chance that he makes. Oh, except we're trying to find out the probability he will miss his next 3-point attempt. Okay, so let's see if I can word this in a way that will make sense. Missing means not make. So if he will not make the 3-point attempt, we can rewrite that as 1 minus the probability he will make the 3-point attempt. So I can then write 1 minus the probability that we have seen that he will make his 3-point attempt is 7 out of 19. I can create common denominators. 1 turns into 19 over 19 minus 7 over 19. And so 19 minus 7 gives me a final probability of 12 over 19. Last slide for this video. Create a probability distribution for rolling 2 dice and adding the results. Picked a good one to end on. All right. So, as you may know, each die, since we're rolling 2, each die has 6 possible outcomes. Now, we know that there are 6 possible outcomes for the first die and 6 possible outcomes for the second die. So this means we will have 36 outcomes in our sample space. Here's what all of the outcomes look like. Here you go. That's a lot of outcomes. So we could either roll a 1 and then a 1, a 1, a 2, a 1, a 3, a 1, then 4, a 1, then 5, a 1, then 6. Or we could roll a 2, then a 1, 2, then a 2, so on and so forth, all these values. All right. So now we were saying we needed to add the results of these. Okay. Well, what happens here is we need to do the following. We can notice this pattern here that on the diagonal, so I'm going to start here, on this diagonal we get a sum of 2. 1 plus 1 is 2. On this diagonal here we get a sum of 3. So that's 2 plus 1 is the same thing as 1 plus 2. They both give you 3. On this diagonal here we can see that we have sums of 4. And this trend continues all the way through the rest of the table like this. Here you can see all of the diagonals. So we have a diagonal that sums up to 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So the sample space is all of these rolls. However, our probability distribution, or the events that we could have here, only amount to these values right here. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So we have to make a probability distribution based on these values here. So I'm going to set this up in the following way. So on the left side of this table are all of the events that could happen. Okay? And on this side of the table, we will have the probability that we roll that value x. So the probability we roll a 2 here, there's only one way to do it out of 36 possible outcomes. So the probability of rolling a 2 would be 1 out of 36. So let's see, we can say the probability of rolling a 3, there are 2 possible ways that can happen out of 36. So that would be 2 out of 36, which simplifies to 1 out of 18. How about 4? How many different ways are there to roll 4? 1, 2, 3. I see 3 numbers, or 3 possible outcomes in this diagonal. So 3 out of 36 will be this probability. And that, if you reduce it, becomes 1 out of 12, 1 over 12. And we can continue this all the way down. 5 is 4 out of 36. 6 is 1, 2, 3, 4, 5 out of 36. 7 is 6 out of 36. And so on until the table has been completely filled in. Now I promise you, you go through and add up all of these 36ths, and all of these probabilities will add up to 1. And this is the probability distribution for rolling 2 dice and adding the results.